So I think we can start now. So welcome everyone to this integrated building design webinar. My name is Oscar Bruce. I'm a research fellow who actually recently joined ID for working on urban heat and urban climates. And I'll be chairing this session. So for those who are not aware, at ID, we basically pursue a better understanding of the link between the built environment and health. And this not only involves interdisciplinarity, but also working across scales and amongst other things, what we call also system thinking. All of this allows us to understand how different elements in the built environment interact to create buildings and spaces where people can live healthy and fulfilling lives. And you'll see how our talk today and our invited speaker basically fits well in this regard. So today I'm happy to receive and welcome Julie Janiski, who's a partner at the Boston's firm of the consultancy company Buro Happold. She has been leading multiple integrated teams through her career there and involving knowledge in a variety of disciplines from engineering to designers or even subject matter experts, among others. Her latest project, the house at Cornell Tech, that she'll be talking about to us during the next hour, is an example of her capacity to bridge between scales and knowledges by integrating the building design into the desirable, sustainable urban environment of New York City. This pioneering project enabled the building of a 26-story high-rise residential building granted with the Passivhaus label. We are therefore very excited to hear more about it here, and especially since we consider that her project is an important illustration of our research efforts that tries to improve its building design by integrating as much as possible the multiple dimensions that will make not only a sustainable building, but also a sustainable city. So the floor is yours, Julie, and welcome.
Thanks very much, Oscar, and thanks everyone for joining today. I should note that while Oscar noted that I'm in the Boston office of Buro Happold in the United States, while I was working on the house at Cornell Tech, I was still in our New York office before I moved up to Boston about 4.5 years ago. I'm really excited to share this project and thought it would be interesting to take a look at it from the lens of where we were at that point in time, almost 10 years ago when we started this project, to today, what's changed in the context of sustainability and in the world, and what the goals are that we're all striving to achieve currently, as well as some of the information specifically about the case study, about the building itself. So as Oscar noted, this is predominantly focused around the house at Cornell Tech. That is the tower here on Roosevelt Island, which is just east of the island of Manhattan. And this was part of phase 1 for the Cornell Tech campus, which also included a number of other buildings that you can see here. And some of them were still in construction when this photo was taken. So in 2013, we started the design process with the client. And at that time, one of the sort of newer pieces of work that had come out in New York around green buildings was this study, which was featured in the Wall Street Journal and was attempting to be able to share the topic of sustainability with resiliency. So Hurricane Sandy had just happened. There was a huge power outage, and everybody wanted to try to understand what was feasible with a building to be resilient, to offer a safe and comfortable space if the power actually went out. And the findings of this study was showing the pretty significant delta between some of the older styles of buildings or more robust styles of buildings compared to an all glass high rise, because that was so prevalent and still continues to be so prevalent in terms of new construction. The all glass typology heats up a lot faster in the summer and becomes more uncomfortable, and it loses a lot more heat in the winter and becomes more uncomfortable. As noted, this was coming out of the urban green study, which reiterates some of those pieces, and I'd encourage you to check it out if you're interested, although noting it's becoming quite old at the moment. When we were working on this project, we started by looking at what the context of some of the goals were, both for the city of New York and the state of New York. The state of New York had a climate action plan for 2050 that had been put out in 2010. So when we looked at it for this project, we were trying to understand if the goal is to get to 55.4 million metric tons of carbon per year, then the one scenario or the two scenarios that get closest are those in which the new construction for residential and commercial is zero carbon. So that was a helpful starting place and something the owner was very interested in understanding what that meant for this project. The New York City had also begun its campaign around One City Built to Last, One NYC, which was combining greenhouse gas inventory with the plans that the city was putting together to try to address climate action and climate change. So in this chart showing that 71% of the greenhouse gas contributions in New York are its buildings, and 34% of the entire pie is residential buildings. So this high-rise residential building had quite an opportunity to be able to inform the development of the residential space in the city. At that time, New York City had just recently been collecting data through Local Law 84 to be able to start to collect what actual performance looks like for buildings, and therefore use that information moving forward, which has more recently been enacted through Local Law 97, which is setting specific carbon thresholds, and we'll touch on that later relative to the Cornell project. Pulling out the residential data from that data set at the time meant that we were looking at the types of median buildings that were in the high 130s to 140 for an energy use intensity compared to what the Passivhaus requirement was, which is 38.1. So we also used this graph at the very beginning of the project to show that the intent of Passivhaus is in fact to reduce the energy use in the building significantly compared to average buildings. Fast forward to today, and we all know that the scene around climate action has changed significantly. There's been a huge amount of effort on this in the past few years, which is extremely exciting to see and to actually get to work on and be part of. And that includes a couple of renewed focuses. Here, a snapshot of regenerative design. So moving from doing less harm to doing no harm to now really trying to understand how to give back, how to regenerate nature, equity, and improve quality of life for everyone. And interestingly, I threw in that the iPhone came out in 2007 because I think it's always interesting to remember just how recent that piece of technology is and how much it's completely changed the way that we all function. And if that's feasible, then I think there's a lot of opportunity for individual technological innovations to continue to shape the way that we're approaching climate change and climate action. There's a renewed focus on holistic decarbonization. So in addition to understanding operational carbon, which in this graph is the blue bars, there's also a focus on embodied carbon, noting the yellow bars, noting that by 2030 for new construction, 74% of the carbon emissions will be from embodied carbon. And that's a huge, huge opportunity for the industry to be able to rally around what can be done and what needs to be done in that space to address the impact from the physical materials of the project itself. Corporate commitments have been renewed and or started by so many different firms and companies across the world, Buro Happold included. We've recently published our third global sustainability report and made specific commitments about our own operations in addition to what the carbon commitments are, and many other sustainability themes for all of our projects. In this case, carbon, both operational and embodied, as noted. New York City and New York State have both been doing a significant amount of work since we started the Cornell project in New York City. They've recently announced a gas ban to ban gas in new construction. This article is specifically about the kitchen, but it's gas use overall. The mayor just appointed a couple of days ago a new group of folks to lead a climate leadership team. The city of New York was the first city to put forward alignment to the Paris Agreement a number of years back, and that was building off of the city's roadmap for 80% greenhouse gas reductions by 2050. In the state of New York, there's an ongoing effort around climate leadership and Community Protection Act, and that has a number of goals, some of which are summarized here. Last but not least, in terms of some of the ideas around this renewed focus for what sustainability can mean and should mean, is the growth of Passivhaus certifications worldwide. So this is a snapshot from the Passivhaus Institute as of January 2022. So lots of really current data, which is great. The dashed line is approximately when we started the Cornell Tech project. And it's amazing to see that the number of Passivhaus certifications has more than tripled since we started that project. That brings us to the idea of people. I think in any systems thinking type of approach, or any kind of integrated design approach on a project, first and foremost, we need to think about the people who are designing, constructing, the owners, the occupiers, the neighbors, the folks who run the city and manage the buildings department, really anybody, and the extent to which the project can improve their experience, the health well-being of all of us, equity, awareness, growth, etc. So I wanted to take a few minutes and touch on what some of the aspects of people for this project were, to lay that out. The goals from the owner are what's shown on the page. So while saving the planet was high on the list, I wanted to note that the idea of better living quality was actually first and foremost on the list of goals for the owner, and then do that without having any kind of negative impact, or having a lot less negative impact to the environment. Thirdly, elevate the university, and fourth, save money, which was really looking at operating, building and operating the building off of a generally affordable housing model, to be able to make sure that it remained affordable for the students and faculty at Cornell. The indoor quality is reiterated, I think, by the actual built product. This is an example of one of the studio apartments in the project, with windows looking over the bridge, triple glazed windows, which mean that when you close it, the sound from the bridge is next to zero, which is really, really phenomenal to witness. And spaces that we think are really nice and very, very comfortable, both acoustically and thermally. The team to create an integrated team is a combination of those folks on the screen at the moment, in addition to many others. So I know in this recording, apologies to anybody who was working on the project and I didn't get your logo on the slide. But I think the takeaway here, one of the takeaways was that for everyone on this slide except Stephen Winter Associates, this was our first Passivhaus project, and it was going to be the world's largest and tallest Passivhaus project. It was a really steep learning curve, and it was extremely exciting to be at the table with a group of people who were all willing to really put their heads down and figure this out together. Stephen Winter Associates was brought on after concept design to support the team as the Passivhaus consultant. to operate the model and guide the development of the design with the architects, Handel architects, the engineers, us, Buro Happold, the contractor, etc. I think it's also important to acknowledge that there is some really interesting stories along the way related to people. In the case of this project, the photo shows myself and David Kramer. David is the CEO of Hudson Companies, one of the equity partners developing the project. And at the first meeting that I went to, one of the very early concept design meetings for the project, we were all talking about what the goals for the project could be. We raised Passivhaus as an idea, and David said, well, has anybody done Passivhaus at this scale? And I had printed out this press release, which had come out 2 weeks before that meeting, and slid it across the table and said, in fact, there's a 20-story tower in Vienna that was just published. We should take a look at this as a case study. And he said, well, that's incredibly interesting. I'm going to be in Vienna for my vacation. Later on this summer, I'll go check it out. And he ended up hiring a local Passivhaus consultant in Vienna to take him to not only this project, but 3 others, so that he could see what the buildings looked like, how they're operating, what the people living in them thought, working in them thought in this case, and came back and essentially said, all right, we're going to do this. This isn't a huge obstacle. It's not something where people feel like they're living in a laboratory. This is really great. We're going to do this. And it turned into this, where the owner, the architect, the engineer, the contractor, the subconsultant, the subcontractors, everyone was at the table when there was a big decision to be made to make sure that we were all on the same page and that it wasn't compromising the Passivhaus certification goal for the project. One of those really interesting moments in terms of everybody working together was to address some of the questions that we needed to with the city of New York, where the building code at that time had a number of prescriptive requirements that didn't align with the design objectives of the project. So from left to right, the first was refrigerant charge, where the next version of the code was in line with what we needed to have in place. So that was a very straightforward one. The second one was ventilation rates, where the Passivhaus standard sets up a continuous and boost mode. And that didn't align with the idea of continuous exhaust that's prescriptively required in the code. Long story short, this project for Cornell was not able to achieve the boost mode criteria because of the cost of all of the individual dampers for every single point of supply and exhaust in the building. So instead, it found a compromise between the boost and continuous levels, and that was actually an easier conversation with the city. And then thirdly, the city prohibits the combination of toilet exhaust and other forms of exhaust. So we went to the city to say, we do actually need to combine those sources in order to maximize the amount of energy recovery that we're getting out of all of the exhaust from the building. But what we can do is keep all of those exhaust risers separate the entire height of the building, which you can see in this diagram, and we will only combine them when we get to the energy recovery ventilator itself. And by having a conversation with the city to help them understand why we were wanting to do this, what the kitchen exhaust actually looked like for these types of apartments, and what the end result would be, they were very excited about understanding how Passivhaus could play out more in the city, and they wanted to have a conversation to work through these questions. In addition to the intense amount of work that was going on during the design phase, there was also an intense amount of work going on at the sort of transition from the design to the construction phase. Some of our colleagues on the construction side, the super in the photo here is just an incredible person, despite the fact that he looks very dubious about that tape product. And there was so he had a mock-up in the construction trailer of all of the different types of tape so that he could onboard the subconsultant, the subcontractors as they were joining. And the design team, which the architects are phenomenal about talking about, put together this detail with a couple of other consultants to determine how to actually install the mega panels of the facade to the building structure while maintaining the continuous air barrier, which was something that everybody felt was basically impossible to do until somebody came up with the idea of this single item right here, which is a piece of tape that still has the sticky back on the back of it, so that when the mega panel is brought to the site, that tape is still loose and can be brought over the connection and then sealed by the staff on site. And it was that moment that allowed for the type of continuous air barrier that we needed to have for the Passivhaus project. So I think there's so many little details and stories about how all of the individuals on the project really went above and beyond to make sure that we could figure out how to make this happen. I think that's absolutely critical to the success of the project. And last but not least, the occupants of the building. There have been a number of articles, a number of conversations. The students have reported having less issues with allergies and asthma. The faculty, including this gentleman who was interviewed, say that they absolutely love it. They're saving money on their utility bills, and they think it's really cool to live in a building that is attempting to really move the needle and do something different. On the climate side, we know that there's not just carbon as a focus. That will be the focus of this section for this project, but acknowledging that obviously there are many other topics to cover under the climate umbrella. There are also many tools and standards out there in terms of third-party tools and references. This project attained Passivhaus as well as LEED Platinum. Passivhaus is the focus for this section, but an acknowledgement here that there are a lot of different themes that many of these rating tools are seeking to address. And Passivhaus is largely looking at operational carbon, health, well-being, and a little bit on the water side. There are other rating tools that are aiming for a little bit of everything. LEED is one of them, which was therefore a really good complement to the Passivhaus target for the project. This is not my image. It's an image of someone else took of thermal data from a row of houses in Brooklyn. And I think it's a great image because it shows how much energy is moving in and out of, and in this case, out of in the winter, these houses compared to a brownstone that had been renovated to Passivhaus standards and therefore was holding on to the energy and not letting it move out of the building as fast as all of its neighbors. Another way of thinking about Passivhaus, this is one of my favorite diagrams. Again, it's not mine, but I think a really nice analogy to explaining what the goal of Passivhaus is. So on the left-hand side, a coffee pot that is really well insulated. You put your hot coffee in there. It stays hot for a long time because it's well insulated and sealed. On the right-hand side, the active system with the coffee pot that's plugged into the wall. The pot itself is not insulated at all. It's not sealed at all. It has an opening on the top and it stays warm because you're using a bunch of energy to keep it warm. So the same thing is true for a Passivhaus. The goal is to create a very well insulated, well sealed envelope that can hold on to the energy that you've used to either cool or heat the spaces. And for the energy that's moving in and out, make that very intentional and based around ventilation to have an enhanced indoor air quality, in addition to a more stable thermal condition and therefore thermally comfortable. Passivhaus is an international building standard. The key goal, as noted, is to significantly reduce the heating and cooling loads and therefore the amount of energy being used in the building. But it's not just about that. There is a significant amount of focus around durability of materials, of quality of indoor environment, and on the way in which the ventilation system is balanced so that there's no negative or positive pressure in the building. And therefore, if someone's cooking something with a very strong aroma in one of the apartments on your floor, that smell is not being pulled into somebody else's unit because the airflow isn't equal. And that's one of the things that attracted the owners to this standard, because they really wanted to make sure that comfort was not just about thermal comfort, but it also included acoustic, the extent to which smells have an impact on people, etc. So they're really, really interested in understanding all of the dimensions of comfort. On the last slide on an introduction to Passivhaus here, a note about their first Passivhaus premium building. So shortly after we started the process of working on Passivhaus certification for the Cornell Tech project, Passivhaus released a new system where they were calling the traditional Passivhaus certification Classic, and they were adding 2 additional levels, one for Plus and one for Premium, which is essentially moving in the direction of net positive energy development. And to note, the Cornell Tech project is aligned with what's called the Classic version of the certification. We think that the Passivhaus standard has a massive opportunity to impact the pathway to zero carbon for all of our projects, notably in these 2 areas, for reducing the amount of energy needed by having a really great envelope, and then reducing the amount of energy used by having extremely efficient systems with maximum energy recovery. This graph is indicative. The reduction from the passive side on a Passivhaus envelope is significantly more than what this graphic shows. The house at Cornell Tech is really, I think it's one of my milestone career projects in terms of what I learned from it, what it's been able to do for our company, for the city of New York, for Cornell, for the occupants who live in it. It's been such an amazing project to be involved in, and I can't believe it's been occupied for 4.5 years now. So this is a glamour shot of one of the corners of the building, and this is something that you'll see a little bit more of in some of the slides, in some of the next few slides. This is when it was certified in 2017, it was the largest / tallest Passivhaus in the world. I actually don't know if that's still true or if something else has surpassed. I know there were a number of projects that were getting quite close to it, which we all were actually very excited about, to not be the first or the largest or the tallest for very long, but instead to pave the way for lots of other folks to get there. I will also apologize, all of the units are not in metric, but I will say that there is an article on this project that was done with CIBSE, and it's a lot more friendly to the metric units, if that's helpful. So 26 stories, over 350 units completed in 2017, and we think a really elegant solution to what Passivhaus can do for a building. Daytime and nighttime shots, looking at the building, and to the right, a sliver of another building done by Weiss Manfredi Architects on the campus as part of phase 1 as well. The project started with the idea of making sure that the form stayed compact and that the position of the building was oriented due north-south, with the shortest pieces of the footprint being facing east and west. And what we found during early analysis was that rotating the building 90 degrees would have had a 15% increase in the loads on the building. So there's a huge benefit to having it oriented the way that it was. And that's also a big thanks to SOM and the master plan team for the project, who had actually laid out the parcels for the project. The envelope for the project is the key, right? It's the key starting place for everything that we were looking at. So the objectives included a thermally broken envelope, sorry. a level of wall insulation that ranged from R18 to R40 compared to the code requirement, which is R13. The bigger the number, the better for the R values. An average of 24% window to wall ratio for the project, so quite low compared to where we started with the all glass towers. But from the perspective of the folks who are living in these units, they still have very generous windows, big views, lots of daylight, etc. And then of course the airtight envelope with a continuous air barrier as mentioned. So the green line in the diagram is noting the continuous air barrier. The blue line is noting the continuous air water barrier. And then there's a number of additional notes here speaking to the makeup of the mega panel assembly, which includes triple glazing, mineral wool for insulation, which had a positive impact on the embodied carbon side of the project, and a number of other elements here. The envelope being installed looked like this, and I thought this photo was helpful to be able to understand why the insulation and the R value deviated or ranged from R18 to R40. You can see that there's a slope in the construction, in the design of the assembly here, and that slope is where one of the differences in the insulation value occurs. One of the other areas is here at the spandrel, and the makeup of what the insulation is packed behind that spandrel. So the envelope was designed to be mega panel pre-assembled in a shop. So the panelized wall system was a typical panel size of about 9 feet by 36 feet. So like 3 window bays and about 1 story tall. And the windows were pre-installed in the mega panel assembly. So given that all of that was done in the shop, it had an extremely positive impact on the performance of those mega panels from a quality assurance point of view. And this is an image from Handel Architects. Both of these images are from Handel. And the one on the right is a shot showing the mega panel being lifted up to be installed on the building. From a systems point of view, shifting from the envelope to the systems, we did a pretty robust study at the beginning of the project in concept design to understand what all of the different system option types were that we thought were most applicable to the project and in line with the goals that the owner had for the project. Gas-fired PTAC was only studied for reference and comparison. It was not a system that anyone was interested in installing. But then we then looked at water source heat pumps, air-cooled VRV, also known as VRF, water-cooled VRV/VRF, and a valence system. And for each of these, tried to unpack the impact to many, many variables, including energy efficiency, the type of space requirements, where the floor area was needed between the roof and the on-floor requirements, fresh air, thermal comfort, control, acoustics, and cost and billing. We then showed what that looked like in diagrams to make sure that there was an understanding with the contractor and the subcontractor of how the system would generally come together, and also for the owner operators to understand what therefore the maintenance might look like in terms of how many of these things there are and where they're located in the building. The system selected is the air-cooled VRF system, and we ended up laying it out so that one of the key issues with the air-cooled VRF solution was that we had too tall of a building to put all of the condenser units on the roof and feed it all down. We had to have the units either at a number of locations or just stacked on every floor on the project. So with the architects, we identified a location here, which we ended up calling the Condenser Porch, which is from a thermal point of view, an outside space, not thermally enclosed, not 100% water enclosed either, but it does have this metal screen, which was in the other photograph, going up the entire building, which was illuminated and became known as the zipper, which we think is a really cool way to express something that is ultimately supporting the mechanical system for the building. These condensers are connected to evaporator fan units in every single bedroom and every living room, so that all occupants have the ability to control their own space, which was also a priority for the owners. This is that zipper and what it looks like. Here's a close-up so you can see the way that a pretty standard louver was modified with these fins to create a really cool outcome, both at night with the lighting shining on it and during the day with the natural light shining on it. This is what it looks like on the other side of that screen. So this is the space that is technically an outdoor space with the screen in front of it, and this is the condensing unit. This is inside the condensing unit where you can see the exhaust air or the heat rejection component here being connected with the ductwork to the screen to direct that airflow. That outdoor space was facilitated with a thermal break between the slab here for the outdoor space and the concrete slab inside for the residents. So we ended up using a shock isocore product to be able to thermally separate those two pieces of concrete, and that was also necessary to be able to achieve the type of thermal bridging goals for the project and the Passivhaus criteria. The ventilation system, adding on to the heating and cooling system, was to again maximize the amount of energy recovery that we were gaining on the project through an energy recovery ventilator. This is something we also studied in terms of a floor-by-floor approach versus a whole building approach. For this system, we did end up using the whole building approach. So there are two ERVs, large air handling units on the rooftop that serve all of the residential floors. And then there's another ERV, air handling unit, on floor 2 to serve floors 1 and 2 in those amenity spaces. The energy performance of the house is something that was tracked in a number of different ways. So the PHPP is the Passivhaus planning package. This is the modeling tool used to understand how good the building envelope is, how efficient the systems are, how much energy recovery we're able to find, and therefore what's possible in terms of a very low energy use. This is data, the actual information is data collected from Stephen Winter Associates. And as they've noted, the data from the PHPP model is for certification purposes and not meant to be predictive of actual consumption. That might seem a bit odd, but because the Passivhaus standard is ultimately about designing an envelope in systems that can achieve a certain energy use, there's definitely not a promise, because so much of the actual energy use is based on occupant behavior, actual plug loads, and a couple of other criteria that are not controllable in terms of a model done early in the design. So the PHPP showed energy use that satisfied the Passivhaus criteria in terms of efficient systems and envelope. The ASHRAE model is one that was done for code compliance. And really importantly, the methodology for the PHPP and the ASHRAE models have some important differences that end up meaning the same building has this type of difference in result. And some of that comes down to the way in which the Passivhaus model assumes that if it's nice enough outside, residents will open their windows and not use active heating and cooling. And unless the system is actuated and automated, the ASHRAE methodology will not allow you to take credit for that in an energy model. So that's one of the key differences between those two. And then the actual data on the right-hand side of the screen is from 2018-2019 academic year, apologies, and shows that essentially the actual performance of the building is somewhere in between those two. And we think there's still room for improvement as the building continues to operate. Another way of looking at the actual performance of the project is to compare it to the more recent regulations that are coming out in the States. This is showing both the New York version and the Boston version. The Boston version is Buro 2.0 and the New York version is Local 97. These are effectively setting maximum allowable emissions from buildings from current year to 2050. Boston is going to 0 by 2050, and New York is still working out how they're going to handle 2035 to 2050. But notably, the house at Cornell Tech is sitting at an emissions density that means that they're already below the requirements for the reporting years through 2034. So they've got some time to be able to figure out what their next steps are. Some ideas that the team has had are noted here. And importantly, the grid will also continue to get cleaner according to the goals that both New York and Boston have. And that will contribute to the overall emissions density for the project. Last but not least, a couple notes on embodied carbon. We wanted to take a look at the embodied carbon investment being made in a more robust envelope and compare that to the overall performance of the project to be able to have and to be able to know that the Passivhaus investment in embodied carbon made sense. So we studied a baseline envelope that met code requirements and a Passivhaus envelope which showed glazing components that were about 2 times better than code, opaque elements that were about 2 times better than code, and ended up having some results that look like what's on the screen now. On the left-hand side, the embodied carbon results of the envelope alone, showing that the baseline was 24% lower than the Passivhaus envelope, given the additional insulation and window material for the project. Once we combine envelope and structure, that delta shifts to 6%. From an envelope and structure point of view, if we then add energy use and an assumption about the building having a lifetime of 60 years, the 6% delta here for embodied carbon from a baseline building code compliant to Passivhaus shifts significantly once we add in the annual operational information for a code compliant building using this much operational carbon and a Passivhaus building using this much less operational carbon, so that over the 60 years, there's a significant benefit from a carbon point of view, a lifetime holistic carbon point of view, to utilizing the Passivhaus standard to show and find those operational carbon reductions. Oh, sorry, this is the last point around sealing, which is where the other actual information, the other actual data that comes out of the project is the blower door test that's done at the end of construction to show that the building envelope was actually constructed to the level of air tightness required. And in fact, the house at Cornell Tech had results that were 3 times better than what the Passivhaus Institute requires. So it was exceptionally well done, well designed, well constructed, and enormous.
I think we have an issue with the connection with Julie. Sorry, Julie. Yeah, we lost you
No, that's
for.
okay.
Yeah, we lost you for.
Hear me?
Yeah, for 1 minute.
Okay.
Yeah.
Is it good now?
Yeah, perfect.
Excellent. So we used a product called, and this diagram was just for 3 of the many exhaust risers in the project and showed how much leakage there was before we used this product and how much was left afterward. So an enormous betterment in terms of using this product, blowing it into the ducts and sealing up all of the small holes throughout the system. A number of closing thoughts here around some of the key design and construction elements for the project, from code to windows, to fresh air, to analysis, to the actual performance, and ultimately a quote from the dean of Cornell Tech at that time, Daniel Huttenlocker, who has since moved up to MIT, to note that something that we all agreed with, which was that this was obviously a very exciting project for us, but we hoped that it was really going to be able to help show what was possible for green buildings in New York and beyond. So with that, thank you. And I hope that leaves us with enough time for some questions.
Thanks a lot, Jenny.
Yep.
We already have 2 questions from Paul Williams. So I can actually give them the right to speak at the same time. So I will do that now with Paul. So Paul, normally you can speak.
Oh, thanks. I've unmuted now. Yeah, the first question, Julie, was what was the construction period for this building?
Sure. So the construction period was 2 years, from 2015 to 2017.
That was 2 years. And what was the development period?
That's probably a more nuanced question. The project came out of a developer-led competition that was run through the Economic Development Corporation with the City of New York. That process took quite a while in terms of the city working with a number of different institutions, Cornell, Stanford, et cetera, of which Cornell ultimately won. And by the time they got to that process or to that point, they then started to build out the design team. So I would say that the design process, if I'm interpreting your question correctly,
you are,
the different words that we use, the design process was approximately 12 months, but I think there might have been some lag time in there based on the previous competition phase.
Yeah. So in total, then, say 36 months, approximately.
Approximately, yes.
Yeah. My second one, well, actually, it's my third one, isn't it? Was I was very interested in your talk about the inference about embodiment and trying to square that with the heavy use of concrete that seems to have been applied to this project.
Yep.
How did you actually look at the process of, one, the quantum of the concrete, and two, the process of the manufacture of the concrete in making your assessments?
Sure. So the structure for the building was a conversation between steel and concrete. The ability to have a flat plate concrete approach to the project meant that the floor to floor heights were able to be extremely efficient, which meant that the owner was able to get 26 stories under the height limit for the project. So from a pro forma point of view, the developer, the priority and the preference on the owner side was the concrete flat plate design approach to be able to facilitate that efficient floor to floor and ultimately the maximized amount of space and rentable space. The way that we thought about the concrete on the project was to understand the mix type, and the mix type differentiated between the different strengths of the mixes and the different uses of the concrete, from foundation to superstructure to slabs. Excuse me. And we maximized and I apologize, I don't remember the percentage, and I wish I did, but we worked with our structural engineers and the ready mix concrete suppliers in the city to maximize the amount of fly ash and other supplementary cementitious materials, SCMs, in the mix to be able to really bring down the embodied carbon footprint of the concrete as much as possible. So there was definitely a pretty strong mix of priorities and variables being considered. On one hand, the benefit of the project and the units ultimately being able to be more affordable if there are more of them, and therefore an efficient floor to floor height. And on the other hand, the ability and or limitation of being able to improve the footprint of concrete, because we know that concrete has the most dense embodied carbon footprint of the structural materials we would typically consider. Does that answer the question, Paul?
Yeah, you've gone. Yeah, especially I think the amount of work that you must put into determining, let's call it, as you called it, the mix of the concrete.
Yeah, I would say it's very common to not actually, I will say it's becoming a lot less uncommon to not pay attention to this. But I would say 10 years ago, it wasn't very likely to necessarily have a focus on what the concrete mix is and its embodied carbon footprint. We benefited from the work that we had actually just done on my first large life cycle assessment embodied carbon study for a stadium in Atlanta, Georgia, where we spent innumerable meetings with all of the very senior leadership on that project, talking about the concrete mix, which nobody expected to do, but had a really great positive impact in terms of pushing the carbon footprint down significantly.
Yeah, great, thanks.
Yep.
Thank you, Paul. Are there any other questions in the crowd by any chance? I haven't seen any written yet. Maybe we'll leave a bit more time for everyone to answer. Jumping on that, I had a question, Julie, for you. How much? So it's actually a single building that was built in New York of such kind now. And thinking about the compactness of cities, which we are usually aiming at or aiming for more, I was wondering how much space between those buildings would you consider would be necessary for considering the trade-offs between the well-being of people being outdoor also and having space around those buildings and the energetic loss that is related to this opening too. Like, it doesn't have to be numbered or so, but just like a guess or an idea.
Yeah, I'm going to go with the idea instead of the guess. Sure. But I mean, I think it's a really good question, right? You can go back into architectural history and think about the tower in the garden scheme and the way that people were thinking about city planning and urban planning and trying to, like, that question has been such a huge question for so long in architecture and urban planning that I can't have an educated guess. But I do think that from an idea point of view, the Cornell Tech campus was being designed with the SOM team and field operations team, the landscape architects, to make sure that there is a sense of place, to make sure that there is a combination of amenities, so that if you are a grad student living in one of the apartments in this building, you have access to the types of amenities you would expect to have access to. It's phase one of numerous phases. So the design, there was some design effort around making sure that the massing and scale of the open space to these buildings also worked with the future phases. And I think it's also, I would say it's quite different for a campus, right? An academic campus than it would be for a typical urban block. This building has 4 exposures, north, east, south, and west. That does not happen in Manhattan for an infill building, right? Maybe you get north and south, maybe you get east and west. You don't get all 4. So the opportunity for this building to have that much exposure was unique to begin with, much less its access to open space and the type of campus green that's more aligned to campus design than it is to necessarily city design. That said, I will say that the City of New York definitely has some really good information in their Plan YC document, Plan YC 2030, specifically on this question about open space and how much there should be per resident and in what walking distance. So I know that there are people that have really good opinions and information on it.
Okay, thank you.
Yep.
Speaking about the orientation, and you were talking about it, maybe I missed it during the talk, but I was wondering what was on the northern side, actually, of the building, because you basically don't get any energy from the sun there.
We didn't, there was some conversation about treating the orientations differently. And we looked at that from the point of view predominantly for external shading, where there would be a focus on external shading on the east, south, and west. But it didn't have as much of an impact as we thought it would, predominantly because of the quality of the glass and the limited amount of glass on the project. So 24% window wall ratio and triple glazing that was just a really excellent product. On the north side of the building, I think if we had not been doing triple glazing for the entire project, we would have focused on triple glazing on the north side, specifically given that New York is a heating dominated climate. And in the winter, you're losing a ton of thermal energy potentially to the northern exposure without having the benefit of the solar gain. So those were the conversations that I think those are some of the examples of the conversations that were happening in terms of looking at each orientation. The other thing that we did with the mechanical systems was to pair the north and east exposure with the south and west exposure. So to the extent that there would be a little bit of some still in heating and some still in cooling, given much more warming on the solar and west than from on the north and east, that provided a bit of that flexibility as well.
Okay, thank you. We have very rapidly, we have a last question from Alexei.
Sure.
I will read it and make him able to speak so that he can answer when you answer to. Could you comment on the carbon issues associated with the design, manufacture, and use of the elevators, and any work done on ways of encouraging the use of stairs? For example, providing attractive stairs between several floors, both for health and social well-being reasons. In the meantime,
yep. Alexi, it's a great question. I've worked on other student housing projects where it's more about an undergraduate student residence community. And there's a lot more focus on looking at 2 to 3 stories of housing and having a zone of interconnecting stairs and lounge area, so that those so that there's I think that one of the common goals is about 25 students in a group with a shared space, and that's a really key trend in the design for student housing, particularly on the undergraduate side, where they don't necessarily know very many people. It's really about generating community and super critical. Given that this is more it's meant to be graduate students and faculty, and it's apartment style rather than a residence hall style, there was a lot less of consideration for that specific design component in terms of the floor to floor, and instead a greater amount of focus on centralizing the amenity spaces at floors 1 and 2, as well as the 26th floor. So the 26th floor has a lounge area that's got the most amazing views of Manhattan and an outdoor space. So there's about as much outdoor space as there is indoor space, an area for having barbecues. So a focus on trying to have additional outdoor space in addition to what's available at the ground level. And then at the 1st and 2nd stories downstairs, there is a grand interconnecting stair between the 1st floor and the 2nd floor to make sure that in that amenity space, there's not a use of an elevator where it's not needed. But other than that, the project was really focused on making sure that people, making sure that the floor plate could essentially produce as many units as possible. there are stairs and and everybody has access to them, but it wasn't a focus in the main residential section of the building for this project. And Paul, to your point, unfortunately, I don't have the actual cost information to share for this project, but what I will say is that there is an FX foul study that was done with NYSERDA, NYSERDA, and it was specifically looking at large-scale passive house projects in New York City, and generally found something in the range of a 1 to 5% cost increase at that time. There are other studies that have come out since in cities like Pittsburgh and other places that say that maybe there's a cost premium, maybe there isn't. It really just depends on how you design and construct the thing. So it's sort of trending along the same lines as what LEED did when it came out in terms of how people are talking about premiums or not.
Well, thank you very much, Julie, for that. As I was saying in the chat, we will basically close